perhaps are distinctive of Chris as his background. He has tremendous experience in industry. For example, he worked at SBC Communication. You may know this as AT&T today, Technivent Corp, SalesKit Software and Prudential Group Health. And of course, right, he's a prominent computer scientist, and he holds a undergrad degree in English and biology, right? Of course. Of course, was a recipient of the Career Award, NSF Career Award. But perhaps, you know him because he has been the reason why we still have many of the conferences where you want to publish nowadays. Since 2001, I believe, he was the vice president of the TCRTS, Technical Committee for Real-Time Systems. He was vice chair for 2 years and then became the chair. He's just recently stepped down in that role. And so, yes, so the reason why, at least partially, a good portion of the reason why those conferences still exist is for the person who stands right before your eyes today. And so, without further ado, please, a warm welcome for Chris.
It's my honor and privilege to be here, and I would just add that Renato also neglected to say that the whole thing with me being in charge at the top is a pyramid scheme that only works because the younger generation, like Renato, works 10 times as hard as those of us at the top. And if you all want to really have a enriching and productive career, I encourage you to do some of that balanced with needing to publish and advance your technical ideas. But it's a great community. It's really amazing how the whole thing works because of everybody, and it's just been an absolute delight to be part of for, I'm not going to say how many decades. Rich has an idea. All right. So I'm going to talk first. Whoops. For some reason it is not advancing on my.
If you minimize your slides and then click back.
Okay.
Sorry about that.
All good. Okay, that worked. Good, perfect. And there we go. Okay, terrific. So I'm going to spend a bit of time winding up and getting some background in place that all of this hinges on. Okay, so I'm going to talk about Lewin Leyland. Okay, no surprise. The original real-time scheduling paper, right? Rate monotonic scheduling, earliest deadline first. I'm going to talk about Giorgio Patazzo's model, which took that and said, what if we play around with the periods of the tasks and elastically adjust them? We'll talk about Chantem's formulation, where she turned this into a constrained optimization, which basically means that we now have a fantastic hammer and everything looks like a nail. You will see constrained optimization in this talk until you're tired of it. And that's a promise. So parallel real-time tasks. Now you can't even buy chips that don't have at least 2 cores, maybe 4, maybe 8, 16, so forth. And then mixed criticality scheduling, because often even with as many cores as you can possibly wheel up, you might have workloads that are going to want more. And so you have to navigate the trade-offs between different workloads that have to compete for the same even ample sets of resources. Okay. So why do we care about this? Well, there's a really lovely paper from Carnegie Mellon and Toyota folks called Autonomous Drone Cinematographer. What it does is figures out the aesthetics of cinematography as a set of differential equations. And so now you can code, what should my drone be doing in order to follow, in this case, deer. My student Oren Bell, working with Sylvia Zhang and me, connected up these ideas in C++ to a air sim module that has deer roaming around in a suburban setting, okay? And we, of course, call it the deer stalker application. So he's videoing deer. And you're doing pose estimation and all kinds of interesting stuff about their physical motions while the drone is navigating this environment, trying to stay very close to the deer and keep the right angles to have a really good cinematographic framing and not fly into a tree. More about all that. Okay, so how do we start? Well, These are recurrent tasks because we want to be able to timely sense, compute, and actuate, fly, zoom in, zoom out, all the stuff that the drone's going to need to be able to do. And a very natural way to frame this is, what if I did the work to do each of those things on a recurring timer, and I can make some assumptions about this, that it's implicit deadline, which means that I have until the end of my period to get my work done, after which I'm late. And the original version of this is never be late. Okay. Do the analysis up front that says, my workloads fit into my slots that are basically periodic. And so what I can do is make sure that all of at least my safety critical deadlines, don't fly into a tree, mission critical, don't lose the deer, happen. Okay. And if I can do that, I've got a good application. And there's an awful lot of real-time systems that are like this. Okay, now, the world is not as cooperative sometimes as you would like it to be, because sometimes your work ends up just overflowing what you have resources for. And so one of our very first thing we want to be able to do is think about, how do I tell whether or not it works? Well, Lou and Leyland did the math, and they said, okay, first of all, earliest deadline first is a really nice algorithm, which was annoyingly not available on our platform because all we had was fixed priority. So everybody did a lot of rate monotonic. But now Linux, with sched deadline and the budget restrictions you need to make that work properly, gives you a platform where you actually can do EDF with a high approximation of 100% of your resources, minus what the operating system takes away from you. Rate monotonic is interesting because, and I'll come back to this, whether or not the periods are harmonic changes the bound, right? So if they're harmonic, you can get 1.0 out of rate monotonic, and no surprise if you go talk to people like Boeing, which I did in my early years, my dissertation work, they have stuff at 10 times a second, 20 times a second, and 100 times a second. Okay, those are all harmonic periods. Then what happens if you make them harmonic, you get that. But basically what it comes down to is, sometimes even if you had harmonic periods or you're using EDF, you just have too much work, right? So a priority in advance, you say, is my system schedulable? Now, Giorgio Patazzo thought about this and said, but what if you're not schedulable? Could you do something with your workload that would make it schedulable? In other words, can you shrink to fit, right? So you came up with this really lovely physical spring analogy. You compress it, it's actually a system of springs, one per task. Each one has a certain stiffness and a certain range that it can compress to. These are not just perfectly elastic because they have minima and maxima that you compress within. And that all matters, and we'll talk about that some too. Okay, and then you can basically say, you adapt these things. In this case, there's just a weighting factor. E sub I is your elasticity. How much does that task want you to compress when you push all of them, right? So you can think stiffer springs or looser springs that basically compress slower or faster. When you hit the minimum, it can no longer compress anymore, and then you compress everybody else. Okay, so this idea of compression is a really, really nice idea. Even better, Chantem in her dissertation came up with a framing of this as a classic constrained optimization. And by the time I retire, I really, really want to see this paper recognized as being the big deal that it really is, right? This is one of those insights that makes a huge difference. And so how you compose competing constraints from a bunch of different perspectives, including what your application is trying to do, including flight control, which lets you not slide slip into a tree because you got too aggressive in turning a corner, okay? This is a really amazing formulation. So what it's saying is, my compression, so I take my maximum utilization for a given task and subtract its current utilization, and I square that. The distance function, a norm, okay? We'll see norms all over the place. Good news, control theory loves norms. So if you want to bring control theory into this, you can actually compose control tasks with the tasks that are trying to follow the deer, with the tasks that are trying to, switch control modes on you because you're getting too close to a tree and yikes, you don't do that. So there's all kinds of really neat ways that this formulation helps. And then what does it say? It says that utilization of every task, use of I, is between the minimum and the maximum, and the sum of their utilizations is basically schedulable. Okay, and that one for EDF, that fancy formula with the nth root of 2 that the rate monotonic has for non-harmonic, or 1 for harmonic, that's your utilization now. Another observation, these are called sustainable scheduling models. In other words, if you sum the utilizations and they're less than or equal to your utilization bound, you know you're schedulable. Highly convenient for emission control because online summation is really inexpensive computation. You have to deal with stuff that's more complicated and you have to do response time analysis. That's a more expensive computation. We'll come back to that. By the way, I should say, please stop me, ask questions. I'm very happy to interact.
Happy you suggested it. So is this result saying that this gives the optimum?
It is optimal modulo your choice of your weights. So what you're saying is, and your limits. So you have another programming problem which says to optimize some objective function of your application, for example, pick and choose your min and max for each task. Usually what's done is you say, I can't go any faster than this because my actuator won't do it. I can't go any slower than this because I would lose whatever thing I'm trying to maintain, you know, tracking of the deer, for example. And then those E's are kind of like programming a neural net. You don't know exactly what they mean, but the weights come out right and your application behaves the right way. This is absolutely fascinating because it says that the optimization as well as the constraint system is programmable. And we'll come back to this. At the very end, I'll talk a little bit about that because that's actually the most recent work we've got is using control barrier functions and scheduling together in a paper that will appear at RTAS in Irvine in May. That we can actually frame it in exactly these terms.
It's a one-to-one correspondence. If you have a schedule, you have a solution.
Generally, yes. Actually, it's more interesting than that is you have a space of solutions and you have a space of scheduling options, and we're actually writing a proposal that plays with that. So you have this really neat trade-off space actually in that. So. Great questions. And hopefully I'll elaborate on some of these themes as I go through the talk. So feel free to bring this back up again. And I can, talk a little bit about how some of the connections that we've been finding show up from this fairly basic set of initial building blocks. Okay, now one nice thing is you have lots of cores. One problem is you have lots of cores. So these days, right? So it's a blessing and a curse. I've got now a model where I have to worry about not only can I get all my work done, but can a bunch of different tasks potentially share a bunch of cores. And there's a lot of theory that's been developed ever since we've been getting to 2, 4, 8, and more cores per chip socket. By the way, we have a machine that has a single chip socket with 128 cores in it, right? That's more than everybody would need. Nope. Sorry, my graduate students have figured out a way to completely saturate it, and I'm waiting for the next few doublings, hopefully. And so this is really amazing because what happens is not only do you spread them out on these cores, you have end-to-end constraints now, which says I have this most expensive path through a directed execution graph of control flow dependencies, data flow dependencies, or dependencies for other reasons that lets me model this in this way. And so things can't happen until the predecessors have happened. Now I have to worry about not only can I schedule the whole thing on the cores that are there, is there enough resource to use it, but can I schedule the whole thing in the deadline that I have, which is from the first node to the last node. Okay. And then Jing Lee did some very nice work.
Mike,
Yes, please.
I'm going to talk about this later.
Yeah.
As an architecture type person, so how do you handle communication through classes? Because you're going to have, just to go way, way, way back. So like when I was in graduate school, we were thinking of, well, you just don't use cache at all because that way you get rid of the indeterminants.
That's right. So if you want to be highly regular, then that's an advantage. However, sometimes you can't afford to do that. I'll actually later have a slide about earthquake engineering applications that we've used parallel real-time tasks for. We had an older machine that had 2 8-core chip sockets. And once you got outside of a chip socket, your communication costs very quickly just were too much to deal with. So we could go 8 cores, 9 cores, 10 cores, 11 cores. We started saturating how much we could pack in because the communication costs just started getting out of control. And it was interesting because actually the limit was because of that. And so we reached the point where you could do about a 9-story building with linear dynamics in a finite element model with a specimen that was doing damping or something like that, that was highly, it was physically implemented and highly interacted with the rest of the structure. And we could just in a linear model barely keep up on 11 cores. And we couldn't push any further. Now that we've got 128 cores in a single chip socket, we can still get about 32, 33 cores worth of performance out of it. And then we run out of steam. So that's really interesting because the quadratic effect of communication among all those cores, basically with all the threads potentially doing not perfectly synchronized things. There's lots of dimensions to this in the architecture level as well.
Chris, you talk about being able to saturate 128 cores.
Yeah.
In the absence of these effects.
Yeah.
But in cyber-physical systems, you've got to deal with the I/O world. You've got to sense actually.
And that's how we saturate it actually. So we're actually doing a 2-actuator nonlinear model with our friends at Purdue that we're working with. And what's happening is we're running bigger finite element models, right? So we're getting 32 cores at a time for that part of it. But now we have control compensation because of the 2 actuators that has interesting dynamics and interesting interactions. And modeling that using Bookwen and other particle filters, Kelvin filters, other sort of advanced simulation and tracking kinds of things, just blows through what we have.
But it, not wishing to sort of be antagonistic here, but is it realistic to assume that you can keep those cores busy?
Yes. Or that
When you're dealing with I/O?
you're not perfectly going to.
Okay.
Because what you're doing though is you're trying to decompose. And this is part of what we're after is we want to be able to decompose in our FPGAs, GPUs, and these massively multi-core chip sockets. And what we want to do is have things happen at the time scales that that hardware can handle to offload work from the other ones so that we can put other things that are more scalable in that kind of work and the dependencies across it, because the graph turns out to be everything here. Our hunch, which we have increasing evidence for, is we will be able to pack a lot in there, but only like, okay, I can do more error correction in my, in my model, so I stay more physically realistic. Or I can do more on my control compensation so that I'm physically manipulating the specimen in ways that are more accurate. And those trade-offs.
I'm curious to know about the applications because
I'll talk a little
the
bit.
applications that I'm working on, that's not true.
I'll talk about this a little bit. I may even have a picture. I think you have hopefully I have the right picture in this talk. Okay, so simple example. Why the parallelism and the critical path become annoying is you can't just simply take your cores and your work and do a straightforward division. Here's an example where if I have a deadline, and these are artificially chosen in order for this to be a teaching problem here. But if my work is 12 units, my critical path is 3, and my deadline is 6 units, right? Then I need actually enough cores that I can make this all work, which is 3. Because if I just divide the work by the deadline, I get 2, and this path doesn't fit into 2 cores by the deadline. Okay, so it's literally the stick that props your door open and lets the hurricane in. You can't meet your deadlines because of that. And so what's interesting is, so Jing has this really nice formulation that we published way back in 2014, and then used it in some of these earthquake engineering models to essentially get the kind of performance we were talking about. It's a very straightforward, simple model which just says, obey your precedent constraints every task gets its own set of cores, so none of the other ones are interfering with it. And if you believe that, go talk to Renato and Rich, because if you just put them on separate sets of cores, of course there's going to be interference at the cache level and various other places. And then you go further and you do things that are maybe even much more isolated, or you do some arbitration so that the isolation is enforced virtually and all the standard games that you use there. Okay, now watch my time a little bit here. I'm not spending too much on wind up with it. So then the way this works is you end up, each task has its own set of cores, you determine schedulability offline, you run this, it all works great, and it does. Okay, except look what's happening with the cores. CPU 3, there's just, huge amount of wasted stuff, right? So of course, then Kunal and Sanjoy and others in our department went after this and came up with a much more effective model. And then Sundin is a student who Kunal and I co-advised, also said some interesting things that improved on Sanjoy's model. We were very proud of that. And it said, essentially what this comes to is you play games with fitting into these smaller spaces by separating the things that need parallelism from the parts that could be done sequentially, and co-scheduling all the little fragments that could be done sequentially under classic scheduling models like you saw at the very beginning. And that tends to work. The other innovation that some came up with is you also figure out progress frontiers in your graph that says how much span and how much work do I have left when I reach a certain cut across my graph. And that's neat because the idea of following progress through the graph becomes a bit like following the deer through the forest. So in other words, your frontier moves, your path changes, what you have to worry about remaining in meeting your deadline becomes navigable. And that's essentially what Sun's last contribution in his dissertation did.
Would that also apply to conditional?
Yes. We do not play with conditional tests, but that's exactly how you'd approach it, is you have an either or choice. And as I forget who it was, I think it might be attributed to Yogi Berra, when you reach the fork in the road, take it, right? So that's exactly what you do. You pick a path and then you're on it, and you can forget about the.
Yeah, that makes sense.
Yeah. Okay. Now, the last bit of prep work before we get into the actual stuff that I'm here to talk about is this idea that there are criticality levels. And I won't belabor it too much. It's a well-studied area. Steve Vestal kind of kicked this off in 2007 with a pretty famous paper at RTSS. And then others have gone and taken that and applied it. In our case, you can think about it as just follow and record the deer. That's more important than trying to conserve my battery, right? The only reason I care about my battery running out is I can no longer, harass the deer with video. You might lose the drone. That's I have a good story you may have heard from Renato. That also right. So again, that's a cool way to think about it though, because that's economic cost or opportunity cost because you no longer have your nice drone. Okay. Versus what am I using the drone for? Its purpose. I've spent the money, I've spent the time to get the drone working. Now I want to use it to get something out of it. And then finally, don't fly it into a tree because that also defeats both of them. And when you have these criticality levels, it's interesting because what you can do is apply scheduling theory on a per criticality level, and we'll kind of wrap up with that at the end. Okay, so I'm going to talk about some improvements that we've made. I'm going to talk about the constrained optimizations. This is kind of the sweet spot. And if I have time, I'll talk about integrating mixed criticality and elasticity, which is another use of all this. Okay, first thing we did was a more efficient implicit deadline elastic scheduling approach. There's a nice little hack in it that was just worth a paper. So, one of those. And then I want to talk about the constrained deadline part in more depth, and then go into the parallelism. Okay. Original formulation by Potazzo et al. Is to try to go through the compressions and look at what you have, and when something hits its minimum, you go back and recompress everybody else. Okay, quadratic in nature because you could get unlucky, and every time you pick the one that hits its minimum first. except that it's actually ordered. And so you can cheat. You can sort them by how much distance each one has relative to its weight, and then you go through it in a single traversal. So your sorting cost dominates n log n.
Could actually do better because you know, if you know there's a capacity amount.
That's right. And you could actually play games with this in order to shape it. And then for online purposes, this may be even more useful because what you're doing is you're tracking progress and other things like that. So your envelope is dynamically closing in. And we are just starting to think about all the ways to play with this. Jordan Sun, whose work I'll talk about towards the end, is thinking about that with his elasticity work.
You know how in LaTeX there's a spacing between the words and how, no, I'm not talking about the actual text here. There's an algorithm for this spacing is called glue.
Oh, yes.
There's an algorithm for the how you can
The
vary
compression,
that.
literally.
Yes,
Yeah.
and there is a minimum and a maximum that they apply. So there might be similar,
I wonder if they're doing, oh, that's fascinating.
they have to do it fast.
And knowing them, they probably already figured out this. So we probably have been out published by LaTeX, right? Except that they don't publish in our conferences, so we're okay. That's hilarious.
I bet their papers are badly typed.
Yeah. Like I said, this was worth one paper, right? So
A computational LaTeX is not that fast, right?
That's true.
It's pretty sure.
okay. So then what does this give us? Well, it's actually quite nice because if you take the old approach and look at what happens if you use a linked list, a binary tree, or an array, right? You've got some data structure choices for what you do sorting on. And my colleague John Turner, who worked on networking, observed the real-time systems are usually very small problems, right? 50 tasks is a reasonable number. So, you know, we'll talk about that in some later slides, that when you're doing these kind of performance comparisons, don't forget that an array is really inexpensive per operation, even if it's not optimal in its data structure behavior, right? And so turns out that an array does quite well in these cases. Okay, so now I've kind of used up all of our discussion of the sustainable task scheduling models. So let's talk about the constrained deadline tasks. Means your deadline is set to be something other than your period. And that's the constraint on the deadline. And what that means is you can't just sum up your utilizations. So there's this nice response time analysis that is probably, I'm going to claim, the most powerful tool in the toolkit in real-time systems. And if you hang around enough in the community, you'll see this sort of formula over and over and over again. And it's great because you can sit there and just recur on the relationship and obtain a very good solution, usually.
And this should be PTSD from your course.
Right, exactly. So if you had a real-time systems course here, especially with Renato, I'm gonna not be surprised if you've seen this again altogether too many times, right? With me, you'll see constraint optimization too many times. With more classical scheduling theory, you'll see this too many times. And so what you're doing is you're trying to find the smallest value lambda such that the recurrence on lambda is less than or equal to the deadline and gives you for all tasks, right? So. Okay, now, something we've done fairly recently is the search, though, for compression using this idea says that you basically are going to either do an exact search. That means my compression is going to be as good as it can be with respect to my constraints. So in other words, I can find a solution more often under more challenging constraints. Or with my optimization objectives, I can find a tighter fit that optimizes further than other solutions would. Okay, and then that's expensive. We're using a mixed integer quadratic program to compute that, but that's great if you can do it offline. If you have to do it online, you're probably looking at iteration or binary search. And then, of course, because your number of tasks that you're talking about may be smaller or larger, which of those two is the best option matters in different ranges. And there's some, caveats, right? So it's very efficient for online use, but the periods may end up going too far out, right? And we're just talking about period elasticity. Most things that have period elasticity have a dual, which is the computational elasticity. Can you do more or less work in that period? Okay, and those two dimensions of utilization, we play with both of them usually. So you may be basically compressing more than you have to in these because they're not exact. Okay, so what do we see? Well, again, Raspberry Pi, not a very high-powered platform, more computer than you could legally export 10 years ago, though, right? So as again, the small supercomputers we carry around on us. Yeah,
So on the previous slide,
yeah.
you said that on the approximate approach, we might end up compressing more than what we actually need.
That's right.
So that means we will have parts of a period where we're actually doing nothing because
Yes,
okay,
and
wasting computing.
and your answer may be, I can't schedule that.
Oh, okay.
So there's two bad things that could happen. One is you're inefficient if you have a solution, or you might not get a solution.
Because you want to do some compressing that you cannot
Exactly.
do just
That's
because
right.
you didn't find a sweet spot.
That's right. Yes, exactly. Okay, so of the ones that have solutions, then what we saw is that the iterative approach works very well when there's sort of sort of smaller ranges that Lambda can range over. And so 8 milliseconds solve time, 20 milliseconds solve time, these are completely reasonable for online behavior. And then it blows up to 150 because you're not, sort of exploiting the possibility of binary search. But binary search constants are worse because you're doing more work every time you're moving. So 25, 30, and then all of a sudden 40 is better than 150, right? So it kind of
surprisingly well with utilization.
that interesting. And again, this is a 3B plus. This isn't even a 4B, right? So, yep. So this is great because this says on my turtle bot, which is driving around doing stuff with a Raspberry Pi on its back. Then they basically can use this kind of thing. And then if you have to use it offline, it again goes from 10 tasks with, under a second, no problem, worst case, to about a second, to about 10 seconds, 100 seconds, to somewhere between 100 and 1,000 seconds, to well over an hour, okay? And then, that basically means that if you can do it offline, you're going to even potentially scale up in this nasty exponential curve as well, because MIQP is a great technique that is exponential. Okay. Elastic parallel real-time scheduling. There is this really neat idea that my colleagues at Purdue, Shirley Dyke, who used to be at WashU, there was a fork in the road at which the universe could have had her and her husband both at WashU, or her and her husband both at Purdue, and the fork in the road went to Purdue. So Shirley and Chenyang Liu and I worked together a lot when she was still at WashU and got started working on this. This real-time hybrid simulation idea says, because we can do real-time computation of very substantial amounts in very small timescales, what could we do if we had a finite element model for a 9-story building and a 16-core and 2-chip socket machine, which is what we had at the time? Could we actually have a physical specimen whose behavior we don't understand? This is like hardware in the loop, except hardware in the loop, you know what the hardware is. In this, you don't know what this behavior of this interesting damper that Shirley and her students invented is going to do when you simulate the Loma Prieta earthquake with a 9-story building and that damper in it. And so what you're doing is physically realistic simulation. So every cycle, and by the way, millisecond or faster is the gold standard because of the speed of sound, the rate at which propagation of vibrations in the buildings occurs, the physical phenomenon. And by the way, this is lovely because cyber mechanical systems generally have a constant a lot like this, okay? Some multiple or fraction of the speed of sound. And so what that lets us do is every millisecond-ish, or twice a millisecond, or whatever you need to do to make your dynamics of your system be physically maintained by sensing, computing, your control, actuating. You take the specimen, you measure accelerometers and all sorts of cool sensing on it. Take those, propagate the forces it's applying into the finite element model, compute the response of the model, go back to your actuators and apply the actuation on that. Repeat that every short time interval. And the first attempt, we were able to get it to about half the speed we needed to. That was 2013 RTAS. And then a year later, we had it working at speed of sound. Okay, so this is essentially what we're doing. Now, you have to ensure those timing constraints, but you also want to optimize objectives. So it's really cool because what are my objectives? Well, it can absolutely be tracking of the physical behavior, because what if this thing went nonlinear on us? At a minimum, we need to be able to shut down the experiment and not ruin our expensive equipment, right? But, you know, also there's objectives like minimizing the control error norm and other things like that. You'd like to keep going throughout your whole behavior. Look, another constrained optimization. And so what James Orr did, and some really awesome undergraduates, one of whom who played high school baseball with my son. The universe is an interesting place. Basically came up with this nice idea of applying these things in those settings to essentially exploit our fact that we could, as of 2014, do this in parallel, but now we can do it elastically. We can adapt the rates, and then we actually figured out you could either adapt the rate or the work. So if you have an algorithm that could have adjustable amounts, any kind of anytime algorithm is beautiful for this kind of model. So if you get a better solution, the more you iterate, you could say my solution's good enough, I'll stop iterating. That bounds your work, okay? Or you could say, I can keep iterating because I have room to do it in my elastic model, and so I'm just gonna obtain that much better of a solution each time I run, okay? And then what's cool is they said, okay, but now what about these interesting DAG graphs where the span, the work, and the period are all parameters that you could vary together. You can do a discrete version of this, which is really nice because it lets you try combinations in spaces that are discontinuous. And so we played around with that a lot. So we have two papers back to back in 2018 and 2020 on essentially how this same kind of idea works on those models. A little bit of implementation, okay? We had our set of cores. I could fit 10 on a slide. I don't think I know of anything that has only 10 cores, but anyway, should have stopped at 8, but you know, whatever. But this is basically what a federated scheduling model looks like. And oh, by the way, it's really nice to put your scheduler on core 0, right? This is a hack that everybody who's ever played with virtualization does, right? Including Zen. DOM 0, right? Domain 0 is on the CPU 0, and then everything else basically goes up. Now, by the way, this also has 11 cores, so this is a not too unrealistic representation of what at the time we could actually get to work productively, because if we added even one more core, we would be losing out because of the communication costs. Okay. So all this has to do is use real-time signals in Linux, which by the way, are queued. They're never lost. Okay, they're always delivered in order. So that actually matters a lot. And so that, you know, one trick basically lets us figure out that a mode change is needed because somebody said, yikes, I've just overran my budget and I need more core. I need more work. Give me another core. And if everybody else is lower criticality, that just happens, right? So it triggers it. Everybody shifts. The ones that got a core taken away figure out how to compress. And then that basically either adjusts their periods or their work within that. They all can do this in shared memory, and it does work at these millisecond timescales. Yeah.
So you, when will this signal, like, I'm not gonna make my deadline?
That's a great question. Renato is working on questions like that. We had a fairly simple thing, which was just a classic virtual deadline.
Okay.
So, you know, you could
Something softer.
you could do EDF-VD and just pick a deadline and say, when you reach this time, timer goes off, tells you, you know, hey.
Okay.
Yep. But there's much richer versions of that because the progress frontier through the work you're doing is absolutely what you should be tracking, and cyber physically doing that. Like, I'm about to lose my deer, I'm about to fly into a tree, in addition to what's going on my resources. And these dimensions all at the same time, I will argue, can and should be composed in discrete formulations of these constraint optimizations. So each problem has this set of subproblems sitting in it that map out the space of its possible qualitative sets of behaviors that you could design for that.
And this was a user space operating
Yeah,
system.
totally. On top of Linux. By the way, Linux is a pretty good real-time operating system, right? Thanks to Ingo Molnar, Thomas Gleixner, Doug Niehaus, others who got in there and fixed things, right? I mean, this was back when I was a graduate student. You know, you want me to do what on Linux in user space? I didn't exactly say that to my advisor, but you know, that's kind of what my reaction was. And then when we got down into it, it's like, oh, cool. All the low-level straightening out of the threads at the hardware to kernel interface, right, makes a huge difference. And it got better every time. And then eventually the patch, the real-time patch, which did all those things, didn't even have to be applied by you, the graduate student, because it just came in the standard build. But back in prehistoric times, that was, you know, part of the question. Okay, so couldn't resist a little kernel shark trace on the right here, showing it behaving nicely. Signal handling times, transition times are all very reasonable. You know, tens of microseconds kinds of ranges. And this is, again, older Linux, older hardware. We can do much better than this now. Okay. Part 2. All of these things have really, really neat cyber physical applications. And I'm going to talk about a few besides our toy example of deer stalking, right? This is the ADAPT project. The idea is to sit there with a crystal that when a gamma ray burst comes from somewhere because two black holes are merging or something really astrophysically interesting is happening, hits the collector, bounce, 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 bounce. Arthur Holly Compton did his work that he got the Nobel for up at University of Chicago. He became our chancellor. So we say he was, bless you, right? But anyway, Compton effect says photon hits, deposits energy, scatters at an angle that is related to the energy. So now you can go and you get a whole bunch of these things nearly simultaneously because you can't tell. And then you do a reconstruction. There's a pipeline for that computation that's really interesting that has multiple stages. And the choice of, do I go get another photon and run it through my whole pipeline, or do I keep dwelling in a current stage? And my solution is multidimensional in those. And I'll talk a little bit about the Pareto optimal compression adjustments that we made in that. May need to have task periods be harmonic. So simultaneous localization and mapping, your LiDAR is sitting there giving you a view of the world. Your camera is giving you a view of the world. If you want these two to cohesively tell you something together, you need to align them in time. Okay, so again, we might need to make their periods harmonic so that every n time of one of them, the other one gives you a snapshot of the world, right? And then you can relate them. And then finally, subtask level work compression, which was just this past December, Daisy Wong and Marian Sudvarg, that is a FIMS instrument, fast integrated mobile spectrometry. Now, when I got started in the industry, I was actually working at a startup on mass spectrometry. So I had a pretty good idea about what this is. But this thing actually sniffs the air and picks up droplets. And it can tell you where your aerosol plume of the gas leak from your pipeline not only is, but where it's going. So you fly your drone around the edge of this thing and sniff the edges of it and figure out a mapping for it. And that requires you to do compression in sub-stages of your DAG of your work, basically, in order to make that work. So you get interesting physical dynamics of something like fluid dynamics started. And that's a really simple fluid dynamics problem. The dream in the real-time hybrid simulation earthquake engineering thing is to do something like fluid dynamics with structural engineering. So hurricane washing out the pier underneath your bridge, or the Fukushima disaster where you had a tsunami and an earthquake at the same time. Could you model a situation like that and actually figure out scenarios and run them? That's the kind of thing that this potentially could allow. I'm gonna speed up a little bit because I'm getting short on time, but I mentioned these pipeline stages. You can essentially say, I pick a new gamma ray, I do a source approximation, I can adjust either the technique I'm using, which is computationally elastic, or the number of samples that I'm running through it, which again is computationally elastic because the amount of work is changing. And then finally, the number of iterations that I do on refinement. These are all things that I can adjust to fit into a given compression. So we can also offline trim the parameter space and do essentially a worst case response time argument that says, I don't want to lose any more than I have to because I'm going to compress down. And then because I can do more work schedulably, I pick one of those stages and I put the work back into it. So I re-expand in order to come up to the schedulability. And this is Pareto optimal. So you can find surfaces that you can't do any better in any one of the dimensions without doing worse in one of the other ones. This idea of harmonic elasticity, very cool work that Marian started, worked with Sanjoy and Pontus Ekberg, two of the giants of our theory community, and essentially came up with this really nice framing of this thing that applies directly to OrbSlam 3, which is the kind of classic version of simultaneous localization and mapping that you can find in off-the-shelf robotics these days. And this is a nice example of some kind of error in the application level being part of the constrained optimization. You can maintain harmonic relationships, your frame relationships are much more integrated and the quality of your answers you get out of this analysis gets that much better. Okay. Now, it's NP hard. So you have to do offline crunching of your problem, but then you get polynomial lookup cost at runtime, so you can actually use this. And if we then think about this question of flying around a plume of some kind of, gas leak from a pipeline, we set this up with an interesting wrinkle, which says that our span is now a function. Okay, and that's interesting because I can compress a piece of the work in a subtask that's on the critical path, and all of a sudden the critical path jumps to some other path. Okay. And so that's what's going on here essentially. Okay, but otherwise, all we're doing again is sort of, in this case, compressing the computational work to reduce the utilization.
And the reason why you get better F1 score with elasticity is?
This one is actually because we're maintaining the part of the pipeline for the TIMS thing, which I'm not showing here, unfortunately. We're reducing its work because that frees up work for other things that are sort of the more important
Oh, I see. For the detection.
parts of it. So you can think about this as information gain and loss a little bit. And this all goes into some really interesting both fluid dynamics and chemistry, because if you want to do this for not just detecting droplets, but if you want to apply this to other things and say, what am I sniffing? Then that gets even more interesting, right? And there's two competing versions of this, which is fascinating. One is you want a whole bunch more kinds of sensors in this thing, which means the whole thing, gets bigger and heavier, right? That sniffer flies in something like a Reaper drone or bigger, okay, or a manned craft, right? But if you could shrink the technology down and get the sensors smaller and the weight down and the power drain down, you could potentially fly this in drones, and that would be interesting because then you could do drone swarm detection, which is probably practically more affordable and possibly more effective.
You can fly one sensor per drone?
Yep, that's been talked about, exactly. So we're in conversations with the professor who came up with that instrument, basically about like what is miniaturizable and what's not. That's a really cool discussion. By the way, Jeremy Buehler, our colleague, is also Roger's counterpoint on some really cool pipelining hardware optimization of sequence matching for genomics and other things like that. So there's all these kinds of interesting problems that the two of them work on together that also relates to this as well. Okay, yes, that's the multi-actuator. So these two things are pressing on the side independently effectively, though they're coupled in some interesting ways. The classic example is, what if Minneapolis had an earthquake, right? So these tall buildings have connecting things because it's really cold there. You think it's cold in Boston, right? Really cold in the winter. And then people like to walk between buildings without having to go outside. And then from an earthquake engineering standpoint, that couples the dynamics of the two buildings in interesting ways. And so we're now playing with a nonlinear model where we're trying to do these kinds of things. This pipeline is essentially very similar to the pipeline that's used in the pose estimation for the deer. So that's an interesting correspondence, is that in order to do the control for this, you have this thing that's kind of mission level, which is drive it through the situations we'd like to be experimenting on. While you're doing that, don't destroy your equipment, don't destroy your specimen. Though maybe destroying the specimen is a feature, not a bug, right? So these are earthquake engineers. So you'd like to maybe do it without, destruction. So they play around with metamaterials, which are elastically compressible honeycombs, until they reach a point where they compress and don't elastically come back. And then you compress them all the way down and they're pancaked, and that's the end of your experiment.
Or
So-
military application.
Yeah, that's right, exactly. And so this kind of a problem, sort of has similar kinds of structure. And so what we want to be able to do is say, well, criticality has to be observed. Don't destroy your equipment, don't hurt anyone. Try to pursue your mission within those constraints, and essentially optimize the mission within those constraints. And so what you would see in older versions of things like Vestal's work is, if something can't be done, drop the job. Just don't do the work at all. And what Jordan said was, well, maybe, right? You could actually do elasticity to degrade much more gracefully, okay? And so the first thing that happened was, the last time I was on sabbatical, James Orr, who worked on the sort of original elastic framing stuff, in his dissertation, Stephen Harris, who was at the time a brand new student, who's co-advised by Roger Chamberlain and me, we put together this workshop paper for Workshop on Mixed Criticality with the framing for what does criticality look like in that constrained optimization. So now what you can do is essentially say, at a given criticality level Z, at least the top criticality level, the most critical level, always meets its deadlines, subject to compression at each level, which then becomes an interesting function, because you can actually say, okay, well, the idea with mixed criticality is the more critical stuff tries to be nice to the less critical stuff for as long as it can until it can't, at which point it has to take resources. Okay, so what you have is this interesting pattern where you say, okay, I'm low criticality, so I'm gonna up my demand because the big guys are being nice, but then I reach a point where there's some threshold where I'm gonna start encroaching into what they need, so then I back off. Kind of pyramidal kind of structure, right? Or I've been told I can't do anymore because the big ones now need the resources, so then I back all the way off, but maybe I could degrade to a lower level. So this is where we started thinking about this notion of more graceful kinds of degradation. Then what Jordan Sun did was formulate this as a high criticality, low criticality, so only two criticality level thing, with a compression ratio formula phi that does something very similar to our trick that let us sort things. But now what it's doing is actually looking at the shape of the trade-off and using that to optimize effectively, in addition to elasticity, using Tom Fleming and Alan Burns' idea of importance, which then says if you have to start dropping within a criticality level, have some ranking of which is more important to keep around. So you drop the least important stuff and work your way up through until you're adequate. And then the trick that we used the last time I mentioned was, you come down, you compress so that you don't have to drop anymore, If you didn't have to drop, or if you did drop and dropped in importance order, now you have a situation where you're probably below what your schedulable bound is, and then you expand whatever's left to have more resources elastically back up to the bound. And this is kind of nice because essentially what you can do is compute a lot of this offline, but that at runtime, apply these sort of adaptations and really improve the quality, right? So the sort of quality is maintained with the sort of minimum line, the maximum line, and then we're basically saying is as we get more and more elasticity to degrade more gracefully, we can actually end up with better and better solutions. Okay, so. Yeah, missed my deadline, but not by much. Depends on whether you consider the release time to be on the hour or slightly after. But what we've been doing is looking at how elastic real-time scheduling fits into other kinds of problems, right? Cyber-physical systems problems, mixed criticality scheduling problems, other things like that. And so what we're looking at is sort of this question of how can we play with these dynamic adjustments in ways that fit into these kinds of constrained optimizations. I mentioned co-design of real-time control and scheduling. We'll have a paper at our task that is our current direction we're pushing on the most. We want to be able to look at this in terms of system security. So quality of protection is another constrained optimization dimension that you could play with. And then I'm working with a bunch of really good master students right now, doing bits and pieces of a prototype of a low-level hypervisor and operating system framework to basically start putting these ideas into right above the metal on different kinds of platforms, GPUs, FPGAs, and multi-cores. And I'm about to send in a proposal to get funding for doctoral students too. But the master students are great. I only have them for a year, right? That's at most. Some of them only do one semester, right? So they get up to speed, they get good, they do a bit of work, and then they're gone. So, but that's great, right? So in scheduling, we do a lot of that too. So we ought to be able to cope with that. All right. Lots of folks have done all the heavy lifting. I mentioned this is a pyramid scheme. I'm just sitting at the top. These folks have done all the great work. Colleagues at Purdue, undergraduates from Brown University, University of Texas at Austin, and Stephen F. Austin University. Professor Ian Bate and Professor Pontus Ekberg have worked with us. Of course, my colleagues, Kunal Agrawal, Chen-Yang Liu, Sanjay Baroya, Jeremy Buehler, and Ning Zhang have all contributed to these papers that I've talked about. And then a whole raft of graduate students who've done amazing work on this. Questions that haven't been answered? Any riffs on any of this? Yeah.
One question I have now that I've seen the bigger picture, well, right? So when you connect this with control systems, of course, elasticity can help if you're thinking about degrading potential in the control quality. But I can see a connection also with potentially really hard real-time system. Right? Where you compress and then you drop, but you know that you can't drop because inertia.
So way back when, I was thinking about what do I do about all these concurrency problems that I'm seeing? And is there a way to reason about these rationally? And I ended up doing model checking. So I got very interested in state space exploration using Joseph Safakis' IF toolkit and Wang Yi's UPAL tool. And we would run these threading scenarios through and see what happens in the interactions. And what we found out was you can basically break apart the behavior in ways that lets you figure out a transition system that describes the desired behavior, the mechanics of the mechanisms you're working with, the threads and they're pinning the cores and various other stuff like that. And then you put these two together and essentially have interacting automata. And I think that view of what you're talking about is a direction I would very much like to look at again.
Because the more I look at this, the more it seems to me the weakly hard constraint models are kind of a special case
They
of
are.
elasticity. You could come up with a
Yes.
unified theory of elasticity.
That's right. And maybe not have to do model checking, right? The kind of, if I can't figure out anything better to do, fall back on model checking.
Sure.
But then I think I mentioned this to you. I saw this really cool talk that Lothar Thiele from ETH Zurich gave in one of his keynotes at a conference. It was that he has this really messy problem, and he used assumed guarantee reasoning from both ends. So you start with your goals and you work towards your givens, and you take your givens and work towards your goals. And that horribly messy chunk in the middle that you reach is smaller, and therefore you can model check it. And it was a really cool talk that kind of let me see some of how the things we were thinking about could be used in that style. So I think that kind of approach might be tractable.
Chris, let me be a little bit antagonistic now.
Lovely.
Going back to the bit about parallelism and keeping the cores busy.
Yeah.
Back in the 1990s, there was a resurgence in machine virtualization, right? Because if you look at the design of systems, it's a policy versus mechanism trade-off. And by the end of the 1990s, people had realized that they couldn't come up with a policy to keep the resources busy. So they came up with a mechanistic approach to do it, machine virtualization. If one guest OS can't do the work, let the machine be taken over by another guest OS. All right? So it sort of begs the question, as we increase the availability of resources, can we really continue to look at scheduling as a key problem here, or do we have to look at other issues?
Absolutely have to look at other issues. Because what I would like to be able to do is bring the right machine to the scheduling problem. And so what if you thought about this as not chunks of unutilized resource, but as places where a different machine could homestead? What would you do? And with something like Quest, you already have an answer to some extent. You make the machine malleable.
Yeah.
In terms of its, and so this is our real interest in GPUs, FPGAs, and multi-cores, because each of them has different time scales at which they can do the work, different parallelism degrees, different time scales at which they can switch what they're doing. All those different little parameters mean they're quite different machines. And yet what we're claiming is abstractly similarly, we can use them for parallel computation for real-time stuff. And I would like to be able to think about multi-time scale, collaborative kinds of things that use a bunch of different machines that are sized according to what that piece of the problem really wants. At the same time, whatever you get, you get. I saw the most amazing artistic thing, technical artistic thing, in the Reina Sofia Museum at Madrid. After spending a whole day wandering around and walking around and all this, right? So I was pretty tired and my brain was not fully functioning at that point. So I come up to this thing and it's got a camera shining at you. And it's got these sepia toned wheels that basically did a rendering of your face in, okay, fine. That's, old news. Next to it, same thing, pan tilt units, basically, instead of these wheels, with a crushed beer can, a cigarette pack, a crumpled piece of paper, garbage that was found lying around the street. And this thing could show you a recognizable image of yourself. It was wild. It was absolutely amazing because it could figure out how to essentially do pixels out of these weird bits and pieces. That was really, really cool. And so you can kind of say, well, you take whatever you're given, right? Whatever you picked up off the sidewalk and turn it into something that's an expressive representation of what you're trying to show. And I think this is like that. This is amazing that way. I mean, I just love these problems because of that. We keep banging our heads against the wall for a while, and then we'll go off and, get some sleep and come back. And then one of the students will go, hey, what if we did it this way? And so far, there has usually been a way to make something work that just requires the right insight about how it fits.
Well, speaking of wild and crazy, so as a hobby, I am reviewing everything I forgot as a physics major. And it suddenly occurs to me that, has anybody ever tried applying least action to these things?
There's some
in your
things that people have done in
schedules?
control theory on that. So the passivity stuff and other things like that, I think are, and this is way outside of my expertise, but I think those are in that space.
And it seems that you have verging on an infinite number of paths, and you're trying to converge like nature does.
Yeah,
Nature
that's
somehow finds a way to always find the right path. And,
So use equilibrium in some way and gradients.
and the math behind that is so powerful.
Yep.
But it turns out photons explore all the possible paths, right?
That's right. That's right. In a whole bunch of universes at once, right?
All right, I think
Thank you, everyone.
yes, please thank again the speaker.